Hello again, and welcome back to my computer vision channel. Today we are going to talk about CoDETR, the state-of-the-art model for object detection. So this is the Papers with Code website that basically puts all the benchmarks on a single graph, and we can see here that CoDETR is on the very top, so it's current state-of-the-art. It is unbeaten for quite some time, so we can see that some new models are coming out, but they're not quite as good at object detection as CoDETR. So this is a really good model. And this is my plan for today. So today I'm going to just explain main aspects of the algorithm of CoDETR, and then in the next video, traditionally, I'm going to do a full deep dive into the actual source code and all the little details that are so much more complicated than just the algorithm. And we'll start with just the DETR. So what it is, what is one-to-one label matching, how do we do object detection with transformers. Then we'll discuss which problems DETR have, and this is partly what CoDETR solves. Then we discuss a little bit the so-called one-to-many label matching models or convolutional models like original proposal network. And then we start with the actual CoDETR. So we'll discuss how these Convnets are being used as auxiliary heads for the encoder, for the decoder, and then what are the results. Before we start, I'm just going to have a quick look at the abstract of the actual paper for CoDETR. So I'm going to leave the link to this one in the description. So in the paper, they talk about the problems with DETR training. So they say that too few queries assigned as positive samples in DETR one-to-one set matching leads to sparse supervision. And then they propose to use models such as ATSS and faster RCNN, which are these old school convolutional neural networks for working with images for object detection. And then basically they use them at training time to provide this extra supervision signal to parts of that model, to encoder and to the decoder. And that improves the training and makes the overall model better. And in this respect, this model is similar to DINO and DNDETR in that it has some basic foundational model. It has these auxiliary heads that are only being used during training to improve the supervision signal of the DETR model. And then during inference, we can just throw away these auxiliary heads, and we're left with our original model, which is just as performant, just as small. So we really don't add any overhead on top of what we had before by this technique. In addition, I personally had to dig through some stuff to understand what these ATSS and faster RCNN models are, because I'm what you can call a new school computer vision specialist. I've put a lot of time into reading stuff about the transformer-based detectors, but not the old school convolutional models. So in the next video, when I'm going to read the CoDETR source code, we will read the code for these models as well. In the current video, I'm going to just briefly mention what they all are about, simply to help understand like what is going on in the CoDETR. And so let's start with just the original DETR, a reminder on how it works and what is one-to-one label matching. So this is the picture from the DETR paper on how to do object detection with transformers. So we start with a backbone, which can be a convolutional-based backbone like ResNet. It can be transformer-based backbone like Swing transformer or VIT transformer. In fact, as we'll see later, CoDETR actually achieves this state-of-the-art accuracy using Vision transformer, VIT, as the backbone. But in the sort of fact that they're quite similar. So we start with just the original image that comes in from here, just the pixel values, red, green, blue, so 3 numbers per pixel, which are then projected down in the dimensionality and the resolution, but up in the number of features that we store per each pixel. So as the output, we'll have a picture that is much smaller, maybe 40 by 40 pixels, but now each pixel has like 1024 features in it, for example, where each feature is now responsible for detecting dog heads or edges or some letters and so on and so forth. We will have a lot of these more complex features. Then this 40 by 40 image is then passed to transformer. So transformer always expect some sort of sequence as an input. So we basically have to flatten this square image down into one long sequence. Since we sort of lose the positional information, so where exactly that pixel was in the image during this flattening, we compensate for that by adding a positional encoding. And then we pass that sequence through transformer encoder, which is basically the way to enhance image processing quality, where now each pixel has a chance to, like during self-attention, each pixel has a chance to see, to communicate with neighboring pixels. And the output of that is basically the improved understanding of what is in the picture. And then we have the decoder. So now the output of the encoder has the same shape as the input. And we can still think of that as one element here as some sort of representation of the original pixel. Now, decoder input can, each element in the input can be thought of as some sort of expert that is now going to look at the image, communicate with other experts, and actually understand what objects are present on the picture. So the actual input token, input element, is still an embedding vector of size 256, for example. And then in the decoder, we'll have a bunch of cross-attention layers. That's when the queries, the experts, have a chance to communicate to the actual image and see what's in the picture. During self-attention, they will sort of communicate with each other, which is helpful for them to exchange information and to make sure that no two experts are trying to detect the same object. Then again, the output is the same shape as the input, and so we'll typically have 300 outputs, where each output is now just the embedding vector. And to get some useful prediction out of that, we project that 256-dimensional vector using feed-forward network, which is just a dense layer or a bunch of dense layers, and we project that down to 4 numbers for bounding box coordinates, and then 80 numbers for classification. So in COCO dataset, we have 80 classes, and so you would basically predict the probability for each of them. And we also have this special no-object class. Now, the main difference of DETR to convolutional-based models is that we have this intercommunication between the queries, the experts, and we have the special loss that basically makes it such that the model output already contains some object predictions without duplicates. So you can see here that this first expert predicted this left bird, and then third expert predicted this right bird, and then all the other 298 model outputs just say that we're not detecting anything. So we basically can just take this model output at face value. We don't need to do some sort of deduplication afterwards. We don't need to do what is called non-maximal suppression, which is used in old school convolutional-based models. We can just take model output, and that is our prediction. That is our detected objects. Now, in order to achieve this lack of duplicates in the model output, we need to use Hungarian matching loss. So what it does is it basically looks at model outputs, and it has no way of knowing like in what order these outputs need to correspond to ground truth objects on the actual image, because like, I don't know, do we start left to right or right to left? There's no way to know that ahead of time. So what Hungarian matching does is it basically tries all the available combinations. So it will try to connect every model prediction to a ground truth object somehow, under just one condition, that each ground truth object can only be connected to one model prediction, and vice versa. So it will iterate over all such possible permutations, and then it will calculate the loss, and then choose the matching that minimizes that loss. So in this case, it will get connected somehow like this. So this model prediction gets connected to the first bird, and this model prediction gets connected to the second bird. In some more complicated cases, we might see something like this. So here, for example, the model has predicted 3 birds and 1 cat. And so the Hungarian matching loss will connect one bird to ground truth object, another bird to ground truth object, at which point we run out of ground truth objects. So this third bird, which is basically a duplicate at this point, has to be connected to something, which will be this no object class, which means that the model will suffer classification error from this connection. The same for this cat. So this cat, there's no cat in the image, so this is basically a phantom object being detected. Again, this is getting connected to something because we still have this condition that one model output has to be connected to something. And again, we will suffer classification error for detecting something that is not there. So this is how this Hungarian matching loss makes sure that we don't detect phantom objects on the background. We don't detect the same objects twice. So this is really the core of the Detr model. Now, the actual loss used is for bounding boxes. So we have just classical mean square error, where when we have the detected box, and when you have the ground truth box, and we basically just compute the distance from, I believe, from the upper left corner and then the down right corner. We also have the IOU loss, or rather the GIOU, which is the differentiable version of IOU, which now compares the intersection over union. So now we want to predict ground truth box as close as possible to the original. And the IOU loss works better for small objects because it's like independent of object scale, basically. And then for classification, we have cross entropy loss. So now let's talk about what are the problems with Detr, what are the problems with this training scheme. So the first problem, or other manifestation of the problem, is that the actual training speed is quite low, so it takes a lot of time to train it, convergence is poor, and in the original Detr that led to inferior accuracy compared to old school convolutional models. And the reason that happens, like one of the reasons, is that the positive signal is quite sparse. Now, let me demonstrate what I mean by this. Now, imagine a classroom in a school, and you have a bunch of students, you have a teacher, and then the teacher asks something like, what is the capital of Great Britain? And then one of the students raises hands and says, London. And the teacher says, yeah, that's London. And so in this scenario, even though just one student raised the hand and gave the answer, everyone else sort of saw that, and everyone else also got to know that London is the correct answer. Now, this is not how it happens in Detr. So in Detr, if we take a look at the scheme again, we'd have some predictions that do connect to some ground truth objects, like bird number 1 and bird number 2. And so during actual backprop, the signal that gets propagated back to the actual weights of the model says that, okay, you were correct to predict this bird class, and you get some bounding box error as well, so you can adjust your bounding boxes. But that only happens to 2 of the outputs. Now, everyone else gets connected to no object. At this point, the only signal that you get is that you were right not to detect any objects, and that's it. So coming back to our classroom example, this is the same as like the teacher asking the question, like, what is the capital of Great Britain? And then one of the students raises the hands. Then the teacher takes the student, leaves the classroom, gives him some sort of answer. Then they come back, and to everyone else, the teacher just says that, you know, you were right not to raise your hand because this guy knew better than you. And this is the only signal that you get. So you don't get to know that this guy answered London. You don't get to know that it was the correct answer. This is what we mean by sparse positive signal. Apart from this, apart from positive signal being sparse in general, we also have label assignment instability. So like what you get when you train the model in this way is that every expert sort of specializes, because the experts get penalized for detecting something that someone else has detected, which makes it a good strategy to specialize. So expert number 1 might be focusing on detecting birds in the upper left corner. expert number 2 might be focusing on detecting birds in the upper right corner. Expert number 3 might be focusing on detecting cats. And so they sort of have this division of responsibility, and that's why they don't predict the same thing. But now you have instability. So it can be actually seen that different, like when you train the model, you go through epochs, which means that in one epoch, you pretty much go over the entire training data set. And then on the second epoch, you go over the same data set again to train further. And you can just measure how stable is this assignment. And turns out that it's not really stable, which means that on epoch number 1, this particular expert might be connected to the bird. And then on the next epoch, a different expert is connected to the same bird, which makes it really, really frustrating for learning, because you get this conflict in signals epoch to epoch. And this is the picture from the paper. It actually shows that CoDETR does indeed help with that instability, helps reduce it. Now, there are other problems that are basically dealt with in other models. So, for example, the attention regions in the decoder are not optimal, and the attention is basically all over the place instead of focusing on the actual objects. And this is the problem that is fixed in DAP-DETR. And so we have a lot of models that came after DETR. So Deformable Detr, DAP-DETR, DN-DETR, DINO, which were conceived to fix these problems. Now, CoDETR sort of builds on top of that. In what it does, it's quite similar to DINO and DN-DETR in that it tries to fix the same assignment instability and sparse positive signal problem in a slightly different way. But it's quite close to what is going on in DN-DETR, in that we have this extra training scheme that we basically throw away during inference, and the actual model in DINO and in CoDETR will be the same during inference. So this is the diagram for CoDETR from the paper. So here we can say that this part is pretty much the same as DETR. So it has backbone, encoder, decoder, and then one-to-one set matching as a loss. And then the remaining parts are basically additions from CoDETR that are only used during training. So we'll have this auxiliary heads, which are convolution-based networks. And then they are also predicting something and are connected to some sort of loss themselves. And they also are used to generate some sort of queries for transformer decoder as well, which helps train the decoder. Now, before we dive into that, let's have a quick reminder of how convolutional neural networks work for object detection. So this is an example of how a model like YOLO or original proposal network might work. So first we have some sort of image, and we also project that down into feature space. So here the black dots sort of indicate that we now have a downscaled version of the image, like 20 by 20 pixels, each pixel being represented by this black dot now. And then to get to the actual object detections, we have one pixel detect up to 9 objects, corresponding to basically different aspect ratios that you might have of the object. So you might say that each pixel outputs 9 predictions, where one prediction is like tall and narrow, and then another prediction is short and wide, and so on. And then during training, you also have to solve this matching problem. So you have to connect the object detections or the anchors to ground truth somehow. And like the typical rule for YOLO or for RPNs is to just look at intersection over union again and say that if IUU between the ground truth object and the anchor is above 0.7, then it's a positive, otherwise it's a negative. And so, for example, this anchor is probably not going to work, but then maybe some anchor that comes from this object might work, and so on. The core difference with DETR is that now you might connect many model outputs to the same ground truth object. So maybe this guy has detected the sheep, maybe this guy has detected the sheep, maybe this guy has detected the sheep. And you say that that's fine, let them have it, let them think that they're detecting the object, and let us train them that way. And then for detections that are slightly worse from this guy and this guy, for example, we're saying that, no, that's not a detection, that's not good enough. We're going to say that it's a negative. And so you can see that, considering what we've discussed about the sparsity of positive signal, that it's good in that we now have more positive signal for every image that we look at. But the problem with that is now the model outputs duplicates. And we can no longer trust the model to say that if the model has predicted 5 objects, that there are indeed 5 objects and not 5 predictions of the same object, for example. So in practical terms, to deal with that with convolutional neural networks, we usually just apply non-maximal suppression, NMS, which is the same as saying, okay, if I have several bounding box predictions that are really close to each other, I'm just going to remove all of them except one, because I suspect that it's the problem of my model. But then sometimes that heuristic does not work. Sometimes you really do have a bunch of objects tightly located together in this one spot. So in these cases, the CNNs are basically going to miss some objects. And this is just a small demonstration of how the regional proposal network works. So again, RCNN is basically regional proposal, and then the second part that refines these regions. And so you get the output from the previous model, the one that we had on the previous slide. And the output is some estimation of the bounding box. In here, I show you 2 estimations, one which is quite good, and then another one which is not so good. And then each of these regional proposal will be passed through a separate CNN network to decide if that's a good output, if we need to adjust it somehow, or if we need to throw it away completely. You can see that it's quite similar to attention in that the second part, the second CNN now only focuses on this one piece of image, sort of throwing away everything else completely, which is really helping in CNN to have a better object detection. Now we are finally ready to take on the actual CoDETR, and we'll start with how these auxiliary heads are used for helping train the decoder. So again, this is the CoDETR scheme. Again, this part is pretty much the DETR itself. And now we are going to focus on this part. So now we have these auxiliary heads. So this multi-scale adapter, multi-scale here means that I was actually lying to you. Instead of just one image coming out of the backbone, we typically have several of them with different sizes. So you'd have an image of 200 by 200, for example, then 100 by 100, then 50 by 50, and then 20 by 20. So this is basically different versions of the same processed image with different resolutions and different embedding dimensions. So basically the biggest one is the least processed one, where we don't have that many features, and then the final one is usually the smallest, and it has a lot of features. We have this multi-scale adapter basically to adjust the shapes of this multi-scale output that we have here to be ready to pass into auxiliary head. One thing worth noting here is that we have this sequence output of transformer encoder that is of the same shape as the encoder input. And we can basically reshape it back to the original size, thus arriving at this square image, basically. And that is what we pass as input to our convolutional models. So again, this should come as no surprise to you. A convolutional model is basically a bunch of convolutions, and we're free to apply that to this encoder output instead of the original image or instead of the backbone output. And this is what we're doing here. So we take encoder output and pass that to as input to our convolutions. And then we basically train these auxiliary heads alongside our transformer. So we each of the heads, we have one head for RPN, for the regional proposal network, one head for the regional refinement network, one head for ATSS, and so on. And we basically make them all detect some sort of objects. We connect that to the loss. So here it's called one-to-many label assignments, meaning that one ground truth object is now connected to several outputs of the model, and we train them all together, which means that now we have this positive signal flowing backwards from the loss through the auxiliary heads, through the adapter, back to the encoder. So this connection, well, obviously does not affect decoder because decoder comes later, but this connection here helps us to train encoder, to propagate more signals to the encoder. So once again, auxiliary heads like ATSS, RCNN take encoder output as input. That output is connected to the loss, classification, and object detection, but now we might have one object connect to several model outputs at once. And we use that extra signal to help train the encoder. Well, obviously, because the actual auxiliary heads are going to be thrown away. So the only gain that we get from here is this signal that flows backward during backprop, backward to the encoder. It helps improve us the encoder itself. So here's one of the interesting pictures from the paper that the authors used to demonstrate just how much better it becomes. Now, in this one, I slightly disagree with the authors about the implementation. So here they show the so-called discriminatory scores, where discriminative score is L2 norm of the feature values for that pixel. So basically, from one pixel, we might have 256 feature values, and we basically square them all together, sum them all up, and we get some sort of score. And so it's true that in convolutional neural networks, we might observe that for points that don't really correspond to anything, something in the background, the L2 norm is rather small, so we don't have a lot of features. Now, this is not really obvious for transformers. So one thing that is not obvious is that if there's nothing there, that the features should all be 0. There's literally nothing in the model that explicitly states that. I mean, the model might choose to represent nothing as 1s and then something as 0s and so on. So it's really no way to tell. Another thing that might not be obvious is that one pixel in the encoder output actually corresponds to the same location in the original image. Indeed, because transformers don't really honor the position. They might do everything they want. They might rearrange the pixels, or they might sort of spread the signal from one pixel to all the other pixels. That's really up to them. However, we can see here that in CoDeformable Detr, this discriminatory score map does indeed look more like CNNs. Whether it's good or not, I think is open for interpretation, but this is how it looks like. Next, let's discuss how these auxiliary heads help train the decoder, which is arguably the most important part of the model. And so we have these auxiliary heads, and like for example, for RCNN, in the middle of the model, after original proposal, before the refinement, you have some sort of bounding box proposals. And so the output of the model is also a set of bounding boxes that do correspond to some objects somehow. And during matching, they will either be connected with positive objects, saying that it's a good model prediction, let's train the model to think that it's a good prediction. Some of them will be negative, saying that that's a bad model prediction, let's train the model to do less of these. And so what we'll do now is we'll take these positive model predictions from the final outputs of the model or from intermediate outputs of the RPN network. And we basically will pass all of them as extra queries for the decoder. And this is now this part over here. So we take these auxiliary heads, we take these outputs, only positive outputs, and then we add them to the decoder. Now let me clarify what is meant by that. So this is the decoder. And so the white part is the decoder of Detr. So from the bottom, you have query embedding input, where each token is basically an embedding vector of size 256. So in the original Detr, these were just vectors of parameters that do not depend on the image and are just trained alongside the model. Now, obviously, in the decoder, you'd have access to encoder output that is used during cross attention. And then the output of that is matched with ground truth objects using bipartite matching loss, and this is how the model is being trained. Now, what we do now is we have these extra positive bounding box proposals from our auxiliary heads, and we are going to pass them through the sign embedding. So this is the same sign embedding we've seen before on the slide, so let me get back to that again. So we've seen them on the original slide of DETR over here. So this is the positional encoding. And so in this case, the position encoding takes two numbers, x and y coordinate of the pixel, and then transform them into 256 embedding vector that is then added to the encoder input in this case. Now we are going to use exactly the same technique, but now we have four numbers, x, y, coordinates of 2 points of the bounding box, and we again pass them through the sign embedding to get some sort of embedding output. And we use that embedding output as our input query, and we'll have a bunch of them. And then we can say that decoder output is the same shape as input, so we'll have some sort of queries that correspond to this input. And instead of just feeding that into our bipartite matching loss, we're just going to directly match that to the objects that we have, because we know that this bounding box proposal comes from the matching that we've already done in the auxiliary heads. So this bounding box proposal is already matched to some ground truth object. And we are basically going to say that, okay, well, this query comes from this object, and the output of the transformer decoder has to predict this exact object. So this is how we train the decoder. And now it's better than the original bipartite matching loss that we had, in that now instead of sparse signal where only a bunch of queries actually get connected to anything and get some positive signal, now we have actually a lot of them. So I only plotted two, but you get like several hundred of them typically, because for every ground truth object that you had, you would have several matches with each of the model, and then you have a bunch of models like RCNN, ATSS, and so on. So you have this multiplicative factor, and every ground truth object might have 20, 30 queries corresponding to them, and they all will generate this useful training signal that is direct, that is not using this bipartite matching now. So it does not suffer from the same problems of instability and so on and so forth. So once again, what we do is we take positive proposals, and by positive I mean the ones that are actually getting matched to positive objects in these auxiliary heads, and we feed them into the decoder as queries. So we take these four bounding box coordinates, we apply the same process as in the positional embedding, and that's called the sine cosine embedding. And that converts that to 256 embedding vector, which is now the same shape as just a typical query input for the decoder. And then the output that corresponds to this auxiliary input, instead of taking part in bipartite matching loss, instead we just skip that and connect that directly to the object that we know this proposal is coming from. The process is quite similar to DNDETR, but now instead of doing the denoising task, as in DNDETR, we use proposals from these auxiliary networks. So let me clarify what that means. So this is the scheme for DNDETR. So in DNDETR, what we do is we basically have ground truth object, and we add that as an input by taking the object, again, having some sort of bounding box coordinates for the object. We expand these bounding box coordinates using sine cosine embed into some sort of embedding. But before that, we actually add some noise to that. So basically, we add some noise to the object. Somehow, we expand that into the embedding. We pass that through the decoder, and then we ask the model to remove the noise. So this is the scheme of DNDETR. Now, CoDETR is different in that instead of letting the decoder solve this denoising task, which might be a bit simple and naive, instead we basically take the proposals from CNNs, which are really good, but then they might have a different sort of mistakes. And then we ask the model to improve on that detection. So again, in comparison to DN-DETR, both models add something only during training, so the actual inference will have 0 overhead. DN-DETR doesn't really have anything to help train the encoder, and CoDETR does. DN-DETR uses denoising as an extra loss, which is basically saying that we have an object with a bounding box, we apply some noise to the bounding box, we then expand it using an embedding, and then pass that into the decoder as an input. And CoDETR, instead of using this noise version of ground truth object, instead it uses this auxiliary head proposal, which might be a bit more nuanced, judging by the fact that the model itself turns out to be better. This seems to work better than just denoising objective. Now, finally, let's discuss results. So let me just go to the original paper. So here we can see some performance comparisons with ResNet backbone. So ResNet is not the heaviest and not the most accurate backbone, but it's quite lightweight and it's used in a lot of models. And here we can just sort of compare CoDETR over here with DINO Deformable Detr, which is the previous state of the art, and it's also sharing the same basically inference part of the model. So CoDETR is going to be exactly the same in size, in inference speed as DINO Deformable Detr, but then we can see just how much this thing trains better, and the final accuracy is better as well. You can also see that CoDETR and a lot of other transformer models actually train faster than RCNN, for example. So it takes less looks at the data to achieve the same accuracy, which is also quite good. So we've seen this one before. This is a rather vague picture about, I suppose, how clear the encoder looks after the addition of these auxiliary heads, although the actual interpretation of what is going on here, I think, is open to debate. So yeah, just so you know. So this is the picture of instability in the bipartite matching part of the model. So we still have this bipartite matching. We still rely on that to make the model train in such a way as to not output any duplicates. And despite the improvements in the actual training that we get from this extra loss and extra auxiliary heads connected to encoder, we also can see that in co-deformable Detr, the instability itself is becoming smaller. So even the bipartite matching part of the model seems to work slightly better, although you can still see here that the actual number difference is not that big. And finally, a bunch of experimental results. So here the authors basically test different versions of the model with different backbones. We have R50 ResNet, which is quite lightweight and used in a lot of models. And then other popular backbones are SwinLarge, which I believe was used in the previous state of the art, and then Vision Transformer. And so the actual current state of the art is CoDETR with Vision Transformer backbone. And this is currently unbeaten at 65.9 or 66. So this is like the best model for object detection out there at the moment. So this was it for today. I hope my explanations were clear. I hope it was useful. As always, traditionally, my next video is going to be about reading CoDETR source code. So it's going to be much longer, much more in-depth. I'm going to read the code of these auxiliary heads as well. So if you, like me, never worked with convolutional networks that much, it's going to be quite useful. So we're going to read the code for RCNN, for ATSS, and so on and so forth. So we have a lot to cover. Hope to see you soon.